Hello and welcome back for another presentation in your weather and climate series. This time we're going to introduce air masses and fronts. To understand weather, something that's very important for us to really have a grasp on when it comes with the information is what air masses and fronts are. The names in which they have, the area in which they originate, where they're going, and essentially the type of weather and climate that will be produced long term through the processes that are observed here. We'll also be able to kind of reflect a little bit more on some of the more extreme weather, such as mid-latitude cyclones and hurricanes, which will be a different presentation, but it does have quite a bit of overlap because once we understand how air masses work along with the fronts and when they start to mix and what we can kind of create with that, we're able to observe extreme weather. Well, that being said, let's begin. So there's no better place to start than the beginning, and in doing so we'll talk about air masses and their sources. So to begin, what is an air mass, what is a front, and then we'll move and talk more about the source of where those originate. Now, air masses contain uniform temperature and humidity. They affect vast areas and are named based on the source of the mass itself. So when we think of that, an air mass is a large area of air that we can observe that has similar traits and has a similar origin or starting point. And we'll talk more about that in a moment. Now, fronts are a little bit different. Fronts are actually the boundaries between different types of air masses. So they are spatially limited and they're linked generally to mid-latitude cyclones. So what we'll be able to learn more about fronts is that fronts are the boundary between two different types of air masses. So to kind of talk about the source or the origin. So again, with air masses, long-term heating or cooling of large bodies of air must remain over a source region for a substantial length of time in order for an air mass to form. An example of that could be places, in desert regions, or perhaps in places more like tropical rainforests. So you have very consistent long-term weather styles that will then, because of their longevity, will create different types of sources of air masses. They will also reflect the temperature and humidity of the source region. These are categorized by using lowercase and uppercase letters. So what does that mean? Well, so I'm using this map of North America to really show the variety of air masses and their names. So in our field, in the earth sciences, we can certainly describe what type of air mass or parcel that we're looking at or researching. But same thing with soils and other different environments that we have. It's so much easier for us to give it an acronym or a set of letters and numbers that create a universal language of understanding what it means. So as an example, we can have what's considered a continental polar, which is going to be represented by a lowercase c and a capital P, as you can observe right up in here in Canada. So continental polar refers to an air mass that is cold and dry. They originate closer to the poles and over landlocked regions, which means that there's not a lot of water resources. That idea of continentality and its relationship of that air parcel and mass formation in relation to where is the water in retrospect to that space. We also have what's considered continental tropical, which means it's warm and dry. Those originate closer to the tropics and over landlocked regions as well. We have maritime polar, which is cold and damp, meaning that it originates closer to the poles, but where there's a lot of water present. We also have maritime tropical, which is for warm and humid. Those originate closer to the tropics and over bodies of water. And the last one that we have on this map is continental Arctic, which means very cold. It originates in very, very cold landlocked areas. So that being said, I know I have certainly the codes on North America. I pointed out continental polar, but are you able to distinguish through deductive reasoning the different name and what letter set is prepared for that, between not just the name and the acronym itself, but just by the description. Oh, okay, originates closer to the poles and perhaps even over water. So can you find a place that you think would represent maritime polar or something like that. So to just be familiar with, the names, the acronym, and what it means. The next step that builds onto that, as you'll notice, that there are arrows involved. Now these are this is a very simplistic drawing, and there are seasonal changes, as we'll discuss in a moment. But this is generally the direction in which these air masses move. So you can see that the MP, which is going to be the maritime polar, originates out in the water but pushes into North America. It's traveling eastward, so it's coming out of the west and traveling towards the east. So these arrows really help kind of paint a picture of the direction in which these air masses will continue to move. And then remember, when we talked about fronts, we also can find some of these instances that where these boundary lines where they meet can become a specific type of front that we'll talk about later in this presentation. So I did mention though that the air masses, there can be some change when it comes to our seasons, because we do know that because of not just the Earth's tilt, but the closeness to the sun throughout different seasons, that idea of intensity and duration, that we do have an imbalance of length of daylight at latitudes throughout the course of a year. And because of that, as we know with how air masses are originating, it's long-term consistent type of energy resources and weather, that there can be some change. And so this next slide just shows the different types of air masses, which again we've already mentioned, but I thought it was interesting because it's showing both a summer pattern and a winter pattern, which obviously this is predominantly based off of North American seasons. So we can see that there's a lot of similarity. We find that during the winter pattern that there is an abundance of continental Arctic air that is being originated, but that makes sense because everything above the Arctic Circle is receiving 24 hours of darkness, so we will see a tremendous amount of time of cooling down. So you'll have a consistent volume of colder air. So I just thought this was an interesting way to just see, again, these air masses in motion, and that they are not just sticking around in one spot. That there is motion within them. We know that wind blows, and that wind blows because of the uneven heating of the Earth's surface. So we've got that. We also have the length of daylight, which can affect evaporation rates and add the humidity and stuff like that. So it's a very, very dynamic piece. So I wanted to be able to share this, and hopefully, in addition to with this diagram, it does provide a little bit more of a definition as to what those are, so that way you are prepared in case you have to, maybe you're given a blank diagram and it says, generally throughout the course of the year, what type of air mass is, would you expect to find that originates perhaps in the Caribbean, and you would be able to distinguish, oh, well, that must be a maritime tropical, and you would be able to explain why. So that being said, we wrapped up air fronts and masses, air masses rather, and now we're going to move into air fronts. So what are fronts? Well, fronts separate air masses and bring changes in temperature and humidity as one air mass is replaced by another. Now, that idea of replacement is not as simple as just taking over. There's different ways in which that can occur. One could subside, one can converge, one could merge and turn into other types. So that being said, air fronts are the line, the boundary between those masses of air that can create essentially our dynamic weather. Now, there are 4 types of fronts that are often associated with mid-latitude cyclones as well, as we'll see in a moment. We have cold fronts, we have warm fronts, stationary fronts, and occluded fronts. So these are the main fronts that we're going to be discussing throughout this I've said fronts too many times within this remainder part of the presentation. So the first thing that I wanted to do is I wanted to explain what the fronts are, but I wanted to associate it again with some form of symbol. Symbology is really important in the earth sciences because we're able to then draw these out onto a map, and we're able to then understand. We're able to observe and interpret that map, and just with a very simple drawing, we're able to really see what's happening, perhaps both geographically, geologically, and also climately. So, climately, you know what I mean. So anyway, so we can look at a cold front first. So cold fronts are cold air advancing and displacing the warm air that was already in existence, and we draw out a cold front as being a blue line with triangles on it. We have warm fronts, which is when cold air is being retreated or pushed away from an area and replaced with warm air. Warm fronts are a red line with a half circle. Stationary fronts are unique. So stationary fronts are when two different, a warm and a cold front mass, both exist along the same boundary, and there's really not any movement. They're kind of almost at a standstill. And so that's what we call a stationary front. So as you can see, it's a mixture of both, of the red and the blue. So they're kind of at a head-on moment, and it's not decided as to who will overcome the other. Will it be the cold front will take over, or will it be the warm front? And then the last one is an occluded front. So a complicated process where the surface low becomes completely surrounded by a cooler cold air. Occlusion process can be a cool type or a cold type. So we find that in an occluded front, again, you do have a mixture. It's very similar to a stationary front, but in this case, the colder part of it is actually being is more dominant, and we design that as being a purple line with the half circle and the triangle as well. Now, what's interesting about the before I move forward, the shapes, so the triangle and the circle, this is kind of a fun thing that I would like for you to think about, and I'll answer a little bit later in the presentation, is that there is a correlation with the design of the triangle and the circle. So what does that mean? Depending on which side it's on. So, what does it mean when the triangle's perhaps on the bottom of the line versus on the top? So that's something to kind of think about, and do you think it plays a role on the way that we observe and interpret that parcel? So I have a slide for each type of front, so let's go ahead and work through that. So the first one's going to be a cold front. So cold fronts are, again, marked on a map with a blue line, and the blue triangles are pointing towards the warmer air. So hopefully you got that right. Now, these are often associated with cumulus and cumulonimbus clouds, which will be found ahead of the front, still mixed within that warm air. So I love this diagram. It's very simplistic. So, which side is going to be the cold front? It's going to be the left-hand side. As you can see, they also have the blue line with the triangles showing the direction. The triangle, or the arrow itself, is pointing towards the warmer air. So we're seeing what's happening is that this cold front of air is pushing through, and as it's pushing through, it's forcing that warm air upward. And in that process, that warmer air is going to be cooled down, because we know not only is it mixing with cooler air, but when air is forced upward, that through just that process, that adiabatic process, that when air is being forced upward, it begins to cool down. And in this case, they're showing that, okay, so as this air is cooling down, so you've got this warm air mixing with this colder air, the warm air is being pushed upwards. So then therefore, if there is humidity available, that humidity will begin to condense, will create, you'll hit dew point, you'll create clouds, and then probably create some form of weather, some form of precipitation. So that's a great example. I mean, in this case, the cold front is very cold. As you can see, it's 31 to 32 degrees Fahrenheit, but nonetheless, it's just kind of putting it into perspective. I think this is kind of, again, something interesting to observe, because in the real world, you would not see the arrows, you would not really see the cold and warm front from your observation point, but you would see the development of these type of clouds, and you would see that one side is more clear than the other. And I think that just kind of starts painting a picture that, okay, just because we have a hard time seeing air, that doesn't mean it does not exist. And we can actually start to observe how air moves and how it works and how these fronts work just by looking at the weather or the environment itself. So let's move into the next front. So we'll talk about a warm front. So it's again marked on a map by a red line with half circles on it. And this time the half circles are pointing towards the cooler air, the direction the warm air is retreating to. So these are often associated with stratus-type clouds, overcast skies, fogs, and maybe general rain or snow can be appropriate. So what we see here in this case, again, the warm front is on the left-hand side, and the warm front is actually forcing the cold front down. It's pushing it down. It's going on top of, pushing it down, and as it continues to move up, we can start to see that, sure, you reach that transition in which you have rain-bearing clouds, but then it starts moving into more ice crystals because it's moving at a higher altitude. As we can see, it's what, these fronts are pushing up to 20 to 30,000 feet. But again, the warm front is on top of the cold front. And again, that idea is like who's overpowering what. With the cold front was the one that was in charge. This time, in a warm front, the warm front's pushing it down, and that's the one that's going to be the one in charge, large and in charge. The next front will be a stationary front. So stationary fronts are marked by alternating red and blue lines. Again, that blue and the triangle and the red half circle. This time it says here that point in the directions of the warmer air. So it says that the red line and red semicircles report towards the direction of cold air. So again, same idea as to how we observed these drawings before. But these are considered quasi-stationary, as it rarely ever completely stationary, because air is always in motion. But what it's essentially saying is that you have the cold air on one side, the warm front on the other, and it's kind of pushing back. So it's pushing back and forth, and one has not been able to become stronger or to overpower the other. So, yes, it's stationary, but it doesn't mean it's like a permanent standstill, because things are constantly in motion, as we'll talk about in other presentations, when it comes to just even the fact that the Earth is spinning and that things are deflected to the right, called the Coriolis force. The Coriolis force is where things in the northern hemisphere are deflected to the right. So there's lots of motion that's happening, but generally what we're saying in a stationary front is that not one is stronger than the other, and they're kind of pushing back and forth until one subsides. So those are stationary fronts. The last one is going to be an occluded front. So an occluded front is marked by a purple line with alternating purple triangles and purple semicircles, all pointing in the direction of the frontal movement. So how is it moving? So there are two general types of occlusions. There's a cool type and a cold type. So just by observing this diagram, we're seeing that we have the advancing very cold air, and then we have a receding cold air ahead. So it's not quite a warm air. It's more of a cold front, a colder front moving into a cold front. So that's why it's considered occluded, because it's a mixture of two different types of temperatures. So it's not technically a warm front, that is, but it's warmer than, if you know what I mean. So we can see there is some frontal movement that it does occur, cloud development because of the frontal lifting and the warm, moist air is being pushed upward. But these are occluded fronts, and again, we can see through the diagram, explaining advancing cold air on the left, receding cold air on the right, but the left-hand side is very cold air versus the not so cold. So again, it's not quite a warm front because it's a little colder than a warm front, but it's warmer than the very cold air. So I hope that kind of makes sense. It's kind of unique. So the next part of this presentation is starting to put some of these fronts together to start seeing how, as we have this boundary line in this zone, that we can start seeing essentially, well, cyclones, mid-tropical cyclones and hurricanes. And how does this, you have these fronts that are pushed together in certain environments. We can start seeing all three or maybe even four of them work together to create some form of very large weather system in pattern. So that will be our next part, is the development of a cyclone. So as mentioned before, we're going to start introducing the steps of and development of a cyclone. Now I'm going to kind of jump through this a little quickly, just this first part, specifically because we have an entire presentation set up next that is about the formation, development, and all of the concepts within cyclones themselves, the mid-tropical cyclones and hurricanes. But what I wanted to show within this presentation here is that, okay, we've talked about masses, we've talked about fronts, and then we've also talked about the symbology used to represent those fronts. So how can we see them together, and how do they work together? And I thought this would be a great way to do so. So the first part here that we're going to do is we're just going to talk about the Norwegian model in development of the fronts, but specifically looking at the symbology of both, the warm fronts, cold fronts, occluded fronts, and if needed be, a stationary front. And then the last part will be to look at a weather map and see if, just by looking at the weather map, could we start to depict as to how to find and where those fronts would be. And again, once we understand how the fronts are, we can also look at the air masses and see, what type of air mass are we looking at, and things like that. So, but anyway, let's just first look at this set of diagrams that I've created. What's nice about these is, again, they've got the lines. So as we can see on the left, we've got a cold front on the, we're perpendicular to the page, and then horizontal to the page at the top is the warm front. We also have some great arrows showing just the direction in which things are moving. As we can see, they are connected to a low pressure system, as mentioned before in other presentations. So we know we have low pressure and high pressure. High pressure is when you have a greater amount of force being pushed downward into an area, so it causes things to blow away. In low pressure systems, everything's kind of converging, generally considered cool and unstable, and usually the source of extreme weather or some form of precipitation. So we have this low pressure system here. As we can see, things are kind of moving counterclockwise, and then in this case on the right hand side, notice what happened. The cold front caught up to the warm front and became an occluded front, because they're going in the same direction versus being more stationary where they're fighting one another. They're pushed together, merging into a much colder cold front into a cooler warm front. So again, just kind of seeing how these things are put into motion. Now, again, these are the Norwegian models. What I like about it is two reasons that we're just going to show through. And again, very quickly, because I have another presentation where we spend more time going into the images, but I wanted to be able to see and share with you the cold, warm, and and occluded and stationary fronts, if applicable, how they look in both a superficial view, looking at the symbology, and then seeing it in a 3D view with the different masses. So we've got a cold front with a cold mass behind it and a warmer mass in front of it, and we can see that in this case here, stage one is a subtle boundary exists. We see that this is actually going to be a stationary front because they're pushing, they're moving back and forth, but not one is stronger than the other. Well, that's the stage one. A subtle boundary will exist. A stage two, a wave forms, usually a Rayleigh wave, but nonetheless, we can start to see there's one becomes stronger than the other. So in this case, looking from a surface view, looking down, we've got a low pressure system that's developing in the middle, and we can see things are starting to rotate counterclockwise. So we can see that the cold front is pushing out, and then the warm front is pushing inward. So it's causing essentially a wave, or a turn is starting to develop, which is part of stage two. Now, stage three is when the cyclone begins to become mature. So now the warm air is aggressively pushing in. We can definitely see that there is some rotation that's involved. The cold front is moving, outward. Again, things are moving essentially counterclockwise into one another. So it's starting to create that spinning effect. That is when the cyclone will become mature. Stage four is considered the occlusion process. So that is where we have a very well developed low pressure system that's in the middle. Going farther outward, we know that the pressure is increasing. Again, now the warm front and the cold front at the low pressure point have become occluded. They have now merged together. So now we have an immersion of both cold and warm, which is where you start to develop more of your extreme weather systems, which wrap us up into stage five, which is when the cold air dominates, and now we're going towards the end of a cyclone system, in which it begins to peter out and lose its energy within itself, and that's when the cold air will dominate near the end of its cycle. So again, we'll continue. This is the Norwegian model. We'll continue to talk more about this in a different presentation, but I just wanted to be able to share the idea of how these images, the symbology that represents our fronts, how they look in a weather system. So that brings us to this last part here, which is talking about finding the front. So this is a traditional weather data map that has been collected. We have, again, you can see this is actually a map in the U.S. We've got our states distinguished in the gray lines. We also have on here both yellow and blue lines. The blue lines are solid. They represent pressures. We can see that they've got the millibar measurement on there. Like as an example, this line here has a value of 1002. we can see that as I move, towards this smaller circle, that the pressure is going down, right? So we have a low pressure system here, and as we get farther away, we look for the higher numbers to see where the higher pressure system is being pushed outward and higher pressure is farther away. So it says now how to find a front using a weather map like this. Well, rule number 1 for finding fronts is to look for the strong temperature gradient or change in that temperature. So in this system here, we can look at the diagram. Do we see any design or shape? These yellow lines represent a temperature. So do we see a great difference? I mean, I can see we got 0, 5, 15, 20, then it jumps all the way up to 70. So do we see any design that's a little bit different that may correlate with both the temperature as well as the pressure lines? And then it says, do you see one here? And the next step it says, would you agree that the air mass in the Dakotas is not the same as the one that exists closer to Kentucky? So is the air mass that's more up in the northern part of this map different from down below? So take a moment and just trace with your finger and think, well, where do you think these two masses would be? Do you see any? And on this next slide, I've drawn them out. So do we see two? I can see that there's one here, and I see another one that's down here. I believe that they are very different, and the reason being is that the temperature gradients are different, also the direction in which they're moving. This top one seems to be moving upward, and the bottom one down here is moving outward and around. So I can see there's two different discs or lines that have been drawn. So that's step 1. Now step 2 of the process, it says rule number 2 for finding fronts is a great tool is to look for the dew point gradient or change. Do we again see one here? And if so, is it roughly the same location as the temperature gradient on the previous slide? Well, again, I can see that these lines here are looking at dew point, and I can see that there are patterns. If I just kind of flash back and forth, do we see that it's kind of similar as to where they are? And I would say absolutely, I can certainly see that there is similarities between those two. Now, which moves us into step 3. This is a little more complicated, this map, but you'll see why. Rule number 3 for finding fronts is to look for a strong pressure gradient or change. Strong falls followed by strong rises. Then we move into rule number 4 is to look for the strong wind shift, which is going to be part of the yellow lines. The yellow lines are the wind direction, so actually looking at how the wind is flowing. So I can observe in this diagram that all of this wind is being forced into this low pressure area here. So I can see air is moving up and into, and I can see that this area, this wind here, is moving into a low pressure farther away. So that implies to me this must be a higher pressure zone up in this zone here is the force of moving it. So I'm starting to again see this circular or spinning motion. Now down below it does give a note. It says note in this image the dashed blue lines represent pressure rises while the solid blue lines represent pressure falls. The numbers represent millibars per 3 hours of rise and fall, and the yellow vector or the arrow lines are pointing in the direction that the wind is blowing towards. So it's showing the direction and force. So again, what we're observing here is, okay, we started from just looking at a traditional system, a weather map on the U.S. We're looking specifically at pressure gradient and temperature. Then we move into looking at dew point and type of moisture if available and humidity. Then we look into wind direction, and then we move into the final step, which is the last rules to check: does the cloud and weather patterns correlate or match with what we're seeing? And so that's what this is. The one on the left is a Doppler system. This is using some satellite imagery, so we can see that there is some cloud coverage. And then we move into this last step, which is finding the fronts, is that, okay, this is how it would have been labeled. So we've got your low pressure system, you've got, again, your occluded zone in the middle, you've got your cold front spinning, you got your warm front up at the top, so we can start to see, okay, this is how these weather maps are put together. And it's a very long process. I think the easiest part of this is to look at this that we're seeing here and go, okay, so based on this diagram, it looks very similar to what we saw in this slide, somewhere between these two slides here, looking at our stage 4 of a cyclone, or stage 4 to 5, seeing where the occluded front meets in. So we can kind of see that put together. So it says every cyclone presents unique characteristics. While the satellite and radar may not have shown the front very well, the temperature, wind, and moisture analysis definitely provided a clear clear-cut picture of where this front should be analyzed or observed. The rules for finding fronts should not imply that all these rules need to be met. It means that you need to use them and find the tools as a front to locate them. So it's kind of like the Pirate's Code. It's a sense of, it's a rule, but there's a little bit of gray zone to try to make that distinguishing understanding and identification of what the rules really are. It says often fronts are very subtle, and only one or two of those rules might be extremely useful because maybe they're the ones that have not developed yet. So again, why might that be the case? Well, we have no idea what's happening the time of year. We don't know what type of not looking at the fronts, but looking at the air masses. Maybe it's drier or wetter or colder or warmer depending on the season. Humidity. There's a lot of different factors that can change and make it more challenging to find fronts. But there are, again, those telltale signs that we can use within those steps. So, again, what's the big walkaway is that when we can start looking at stuff like this and go, oh, okay, I totally get it. I can see that we've got a cold front, a warm front. We've got some occlusion happening at the very, very low pressure point up at the top of the map, and that this is the beginning and true development of a cyclone, a very large weather system, and probably once it gets a little bit closer, will produce great amounts of precipitation. So that was really, again, jump into it, talk about it, looking at the introduction of air masses and fronts. The next presentation I'll have shared for you will be dealing specifically with mid-tropical cyclones and hurricanes, where we spend a little bit more time about the development of that extreme weather. I hope that was helpful. Be sure to comment below if you have questions, concerns, or anything you want to mention or share with us. I hope you get a chance to like this video. If you have not yet, don't forget to subscribe, and we will talk soon.